Hi, I'm Gioia Falcone, and I'm very pleased to be here to give this contribution to the ITB Geothermal Workshop 2021. I will be talking today about the possibility of repurposing oil and gas wells and converting them into geothermal wells. Before I start, I'm just going to minimize this bar at the top, and we should be ready to proceed. So I will be first of all, introducing the general concept of repurposing hydrocarbon wells. I will then be presenting to you some of the very first pilots that have been implemented worldwide. I will then focus a little bit more on the UK, which is where I'm based, presenting to you the results of two screening exercises that we carried out at the University of Glasgow. The first one covering onshore assets, and the second one covering some of the offshore assets in the UK. And then finally, I will be concluding. And at the end of this presentation, we have time for some questions and answers. So let's begin with the introduction of the general concept. Well, the concept is very simply that mature hydrocarbon fields tend to co-produce very large volumes of water. And this water production increases over time, and at the same time, the hydrocarbon production declines. The co-produced water tends to arrive at the surface with a temperature ranging between 65 and 150 degrees Celsius, which therefore has clearly a thermal potential. And this combination of those moderate temperatures together with the large volumes of water being co-produced can potentially be favorable for either producing electricity or for district heating or both. And I do insist on the fact that we need a combination of temperature and volumes of water in order to be able to say that we have enough heat flux for us to be able to make use of this thermal resource. In principle or notionally, we could say that extracting thermal energy from existing hydrocarbon assets could allow us to reuse existing infrastructure, therefore delaying the abandonment expenditure of this infrastructure and also contributing to net zero operations while we are still there extracting hydrocarbons. And one could also say that in principle, an oil and gas operator could hand over the field to a geothermal operator, and this could be done when the hydrocarbon production phase becomes uneconomic. Also, there would be in this model an advantage for the geothermal operator because the operator would be saving the initial expenditure of having to drill and complete the wells and install all the surface facilities. There is also in principle potential for sharing, maybe in a pro rata fashion, decommissioning liabilities. It is, however, important that we don't forget that those liabilities don't just disappear, and at the end of the day, the asset will have to be decommissioned. You're just potentially delaying that decommissioning phase, but I repeat, it doesn't magically disappear. And as promised, I'm going to now show in the next few slides a quick review of some of the first pilots that have been done in the world to investigate this concept. The very first one I'm presenting to you is the one that was done at the RMOTC's Naval Petroleum Reserve number 3 in the US, where an organic Rankine cycle power plant was designed to use 40,000 barrels per day of produced water at a temperature of 77 degrees Celsius. And this led to a generation of 180 kilowatts. And the first unit was put into operation in September 2008. This was the very first system in the world to use co-produced hot water to generate electricity in an operating hydrocarbon field. I know that we don't have time for many technical details today, but the table on the bottom right corner of the slide is summarizing the key engineering parameters for this pilot installation in Wyoming. The second pilot I wanted to mention is the one that was done in the Beijing province in China. This was done in 2011, where power was generated from the produced water stream from the Huabei Reservoir. 400 kilowatts of power were generated for a total flow rate of some 3,000 cubic meters per day of fluid from 8 wells with a surface temperature of 110 to 120 Celsius. And this was a first also in that it was the very first low temperature geothermal power plant ever built in China using fluids co-produced from an oil field. Another pilot is one that was implemented in North Dakota. In April 2016, 2 organic Rankine cycle units of 125 kilowatts each were installed to generate power during a first test in the Williston Basin. In that case, they were handling 29,500 barrels per day of fluid at 98 degrees Celsius of temperature. And please note that in this case, the application was at an EOR, enhanced oil recovery installation, and the water was coming from 2 horizontal wells. This was the first geothermal plant in North Dakota and the first USA commercial enterprise to co-produce electricity from geothermal resources at a hydrocarbon field. So important to note is that depending on the stage of maturity of your field, you might be presented with different options moving forward. There is a difference between dealing with a field which is still producing, albeit mature, and fields which, on the contrary, may have been already left inactive for a while, already suspended, or even already fully abandoned. These are all quite different situations from one another. And for example, if you're talking about the first category of fields, you might be able to continue producing the hydrocarbons while also bringing in a geothermal add-on, a geothermal component into your field. And this could then lead to an opportunity for generating electricity that you might be reusing within your own field in order to make operations greener. And or you might also have users nearby, this would be the case onshore only, I would say, for the use of the cascade or associated thermal energy. Vice versa, if you're talking about an infrastructure which has already been inactive for a while or suspended or abandoned, the first question is whether you can be authorized to do a re-entry, whether you can be authorized to restart activities. You might have to obviously apply for it. And also, should you consider re-drilling into deeper aquifer zones? Should you consider recompleting to implement maybe downhole deep borehole heat exchangers as in a closed loop solution? Or should you drill some multilateral slim holes from the existing or deepened bottom holes? So now coming on to the UK and the screening studies that we performed at the University of Glasgow, I'm going to begin with the onshore focus, and I'm going to present some results from different contributions that we have shared already in the public domain. I'm starting with the initial screening from the total number of onshore hydrocarbon wells in the UK. For those of you who are not too familiar with our situation over here, we have just over 2,000 onshore wells that have been drilled over the years. Those are the red dots that you see on the right-hand side. And then we looked at the status as of when we did the study in 2019-2020, and we separated them depending on whether they were still operating or temporary shut in or still in the drilling phase or already abandonment under the abandonment phase or plugged or where data were not available at all. And then we looked at applying some cutoffs and some screening criteria. For example, we left out those wells that were already at abandonment phase 2 and 3, that is where permanent barriers in all the permeable zones of the reservoir were already in place, and also where the surface installation at the well site had already been removed. We also applied a depth cutoff of 500 meters to very simply reflect the criterion of the UK Renewable Heat Incentive Subsidy Scheme, RHI. the 500 meters are in that case taken as the regulatory boundary between shallow and deep geothermal resources. So we then ended up from the regional red dots that you see there to the remaining blue dots. And we also carried on looking at the bottom hole temperature of those boreholes. And when the temperature was not readily available from previous databases, we estimated it using regional temperature gradients and well depths. And we then superimposed a GIS mapping exercise to map the extent of potential geothermal aquifers in the Mesozoic and Upper Paleozoic basins as defined by a previous authoritative reference from 1986. And this allowed for candidate wells to be selected based on estimated temperature of the co-produced water and also based on proximity to aquifers. So that was another level of mapping and screening. Based on the BHT bottom hole temperature calculations, we realized that there were some wells falling in the range of temperatures greater than 40 Celsius, and more specifically, about 391 had a BHT between 40 and 60 Celsius. About 85 wells had a BHT between 60 and 80 degrees Celsius, and only 17 wells had an estimated bottom hole temperature greater than 80 degrees Celsius. So already we had an initial overview of the temperatures at depth, and that was already enough to understand how many candidates had in principle a potential for generating electricity and how many perhaps didn't. We then also looked at the proximity of these wells to potential geothermal fields and whether they had already intercepted prolific sandstones, prolific basins, and still looking at the corresponding temperatures of those. So as you can see on the right-hand side, that map is showing the relevant basins, the location of candidate hydrocarbon wells, and also the location of potential geothermal fields in purple. And those two purple areas indicating the potential geothermal fields are further distinguished between the 40 to 60 temperature range and the 60 to 80 temperature range. And ultimately, we came out with the four most favorable onshore hydrocarbon fields for geothermal repurposing, based not only on what I've just said, but also based on the production rates. Remember what I said at the beginning, we should not be looking for the temperature only, we should also be looking at the rate with which the water comes to surface with a given temperature. And so you can see in this table the top ranking fields with their corresponding coordinates in BNG system, and also with the production in cubic meters per year, bottom hole temperature, and the number of wells in that field. We then decided to focus on the top ranking field, the Wytch farm field in Dorset in the south, and we zoomed into that particular field to do a more detailed pre-feasibility study. Just to give you some background about Wytch farm, especially if you're not familiar with this side of the world, it is located in the south of the UK, and it's in an area of environmental constraints, which I'll come to later. The figures on the right here are letting you zoom in from the location of the Wessex Basin into the location of the Wareham and Wytch farm fields next to one another, Wareham being a much smaller field, and then further zooming into the location of the oil field infrastructure as well as heritage sites. The Wytch farm is the largest onshore oil field in Western Europe. It has very high water production rates and many more operating wells still today than any other onshore field in the UK. Production is from the Triassic Sherwood sandstone at a depth of about 1,500 meters with an estimated reservoir temperature of 65 degrees Celsius. On the other hand, the smaller nearby Wareham field is producing from the Bridport Sand Formation at some 920 meters of depth. And because of the shallower depth, the estimated reservoir temperature is much less than the Triassic Cherbourg sandstone. It's 44 Celsius. So I forgot to mention a little curiosity fact. Again, for those of you who are not familiar with this side of the world, this site held a record for several years, and that was the record of the longest horizontal well, 5.5 kilometers onshore in a reservoir depth of around 1,600 meters. And that was drilled in 1994. That record was subsequently superseded by other wells. We then took a classic reservoir engineering approach to understand whether the water production was going to be sustainable, and if so, for how many years moving forward. So we applied conventional decline curve analysis, borrowed directly from the well-established petroleum engineering discipline. And we assumed that all the wells that were operating at the time would have remained operational until 2037, which was the end of the concession, the end of the license. As you can see from this picture, we had not only a declining oil production, which is the line in green here on the screen, but also a declining water production as estimated by the DCA. The first thing we looked at, and this was with a previous collaborator at Imperial College, Singh, we looked first of all at the potential for power production. And so we looked at whether that water rate in combination with that geofluid inlet temperature of 65 degrees Celsius could produce power. And based on those estimates, the results were that a network of 1.4 megawatts could be generated. And we only look at one of the Wytch farm sites, one of the separators of the gathering stations. Next, we looked at the potential for combined heat and power, that is power first, as we've just seen. And so this section here with the organic Rankine cycle, and then cascading into a heat exchanger to provide thermal energy to a nearby district heating system, coming back with a reinjection temperature of 44 Celsius. And we realized that yes, there was in principle potential for CHP as well as power alone. And then finally, we looked at exclusively the heat option. So what if we don't try to get the power out first? What if we directly try to feed heat into potential uses nearby? And so we went back to estimating the raw thermal power output based on information we had on those two fields and assuming a potential variation in water output. So we came out with a minimum, maximum, and average thermal power output for these fields, depending also on how aggressive we wanted to be on extracting temperature with a heat exchanger at the surface. And then continuing from this estimate of the thermal power outputs, we said, okay, what could we then do with this thermal power output? What if we look into options for horticulture uses or heating swimming pools? And we knew that there were in principle also options for aquaculture and breweries, but I'm only going to show you here the results for horticulture and swimming pools. So assuming different possible outcrops, we assessed how many greenhouses of an average typical size and how many swimming pools of an average typical size could be fed by such calculated thermal power output. And you can see on the right-hand column of these two tables here on the right, the average numbers per each category, that is greenhouses and swimming pools. Then moving away from the onshore scene and looking at the offshore scene, we realized that already in the literature, the potential for offshore fields in the UK to be repurposed to produce geothermal energy had been looked at. And more specifically, we found a study from 2014 that was mapping the different fields, the names that you see in the center here, against the mass flow rate, their temperature, and the calculated maximum ORC power output. And based on this study, there were some high ranking fields up there, and then the rest of the fields were showing as being able to produce 20 megawatts of power and lower. We decided to rerun this sort of feasibility study independently, and we ran it 7 years later, and we realized that this time gap was going to potentially have a big impact on the estimates of power output. Why? Because in the meantime, most of these fields had already continued to decline. And when I say decline, you have to consider the decline not only of the hydrocarbons, but also of the associated water. At the end of the day, the pressure in most of the systems is declining, and so the water output is declining. And if you're thinking in terms of geothermal energy, the water is your product, is what you're after, but that seems to be declining for most of these wells over time. So a bit of the original estimate from 2014 went away, and we ended up with lower estimates 7 years later. We also realized that in the meantime, many of these fields had walked closer and closer and closer to cessation of production, if not even abandonment and decommissioning. So some of these fields, some of this infrastructure has effectively gone already. So the window of opportunity has gone. And finally, we also realized that for this concept of power production offshore to be useful, you probably need to ask yourself whether your geothermal installation can at least power the platform operations. And please consider that on average, at least in the UK, an offshore platform requires 10 to hundreds of megawatts per year of power. So if you don't hit that threshold, you will still need some other sources of green power to really achieve net zero operations. And so in summary, our findings from the survey of the offshore UK fields were that many of these fields today have a geothermal power potential of less than 4 megawatts. And in order to really assess the feasibility of repurposing of any of these fields, one will need to take into account that, yes, water production declines with time, often. Power generation potential versus operating consumption needs to be considered. What is the age of the infrastructure, and can you guarantee the integrity of the infrastructure for years to come? What is the overall size of the development, and what is the overall number of wells versus the portion of the infrastructure that you might want to continue maintaining for geothermal purposes? What are the maintenance costs to maintain the infrastructure in full or partially still active? Do you have any retrofits to any constraints to retrofitting your facilities? What are the overall economics of your intervention and the payback time? And note that in some situations, you might be suffering from competition from other offshore renewables, for example, wind. And as mentioned previously, remember that the maturity of your project is important, and above all, how close you are to the commissioning and abandoning. Do you still have infrastructure in place? Will that infrastructure be still in place by the time you're ready to start your geothermal project? So now just coming to the overall conclusions from this rather fast and brief presentation, I would like to say that based on our analysis, we think that thermal energy recovery from aging or inactive hydrocarbon fields can be feasible, but of course that feasibility overall depends on characteristics of that particular field, plant design and costs, whether you have users nearby, whether there are the right economic incentives, and ultimately it all depends on the regulatory environment. This is very important, and it is something that varies from country to country. It cannot be generalized. I would like to stress once more that I think it is very important that we don't confuse as a community the terminology delaying abandonment with running away from liabilities. No one should think about running away from liabilities. And if we let the ones running away from liabilities, then ultimately the the public, the taxpayers, will end up having to cover for those, and we don't want that. And specifically for the UK, some barriers are in the fact that well, we know that the renewable heat incentives have not really stimulated a deep geothermal heat sector. In fact, very simply, 0 projects were accredited for subsidies since the program started in 2011. Also, it is a UK government policy not to support fossil fuel heat with the RHI, but it is unclear whether this would also exclude heat co-produced with hydrocarbon production. And in the UK, the Crown owns the right to oil and gas, but the law is silent as to the ownership of geothermal heat. So we don't have an obvious, clear owner of heat. And the oil and gas regulators lack a clear mandate to collaborate with the geothermal sector on these matters. And then specifically for Wytch farm, there are some clear environmental constraints because the field lays in an area of outstanding natural beauty. And even though we might be in principle proposing a green energy solution, it will still have an impact of some sort. So with this, I would like to thank you for your attention. And I would like to now move on to addressing some of the questions that have been raised by the audience, which the ITB supporting facilitators have kindly gathered for me, and they presented them in a series of slides. I'm going to go through them with you just now, trying to address them to the best I can. So the first question that has been put through and has been copy-pasted as asked is, what is your most interesting pilot project? Well, I think that every pilot project is meant to be a pilot and therefore is meant to unveil different aspects of the feasibility of a concept. Some pilot projects make it to also become full commercial projects, some others don't, and some others are never meant to anyway. So for me, simply put, they're all interesting and all of them present opportunities for learning lessons. I would say that we haven't quite seen offshore pilot projects yet, and it might be good for the sector to see whether that is a direction that is to be pursued or not. And then another question, is there any minimum well temperature requirements for repurposing oil wells into geothermal wells? As I mentioned earlier, first of all, let me rephrase this. First of all, it depends on the use, right? So it depends on whether you're aiming at generating power from the operation of repurposing your hydrocarbon wells, or whether you want to produce heat. And if it is heat, what type of end use do you want for this heat? As mentioned earlier when showing the study for Wytch farm, the wells we were looking at had temperatures ranging from just above 40 to some 100 plus degrees, so quite a big range, which means that not all the wells in their case could serve the same purpose. And also something I could mention with regards to power generation, the lowest temperature from which commercial power is generated with an organic Rankine cycle today is still the 70 from water, from a geothermal water, is 74 Celsius, and that's at Chena Hot Spring in Alaska. So hopefully this will give you a feeling for what you need to have from your wells. What are the criteria for an oil well to be transformed into a geothermal wells? First of all, how accessible and how old is your well? Can you guarantee the integrity of the well for years to come? Do you need to consider changing the completions of the well, or can you use it as is? And when I say the completions, I mean anything from redrilling to deepening to doing smart holes from your current bottom hole. And also, it depends on what the well is connected to. Is it connected to an aquifer? Is it not? And what are you trying to get out of it? So vis-a-vis your ambition of what you want to get out of your well, you can then decide whether it is the right candidate or not. In the process of transforming the well, what kind of obstacles could happen, and what are the risks, and what is the biggest challenge? For me, before I even speak in technical terms, the biggest challenge has to do with the regulatory environment. Are you allowed? Is there a procedure that allows you to do this conversion? Is there a procedure that allows you from being, say, an oil and gas operator to also co-produce geothermal heat and power? If there isn't such procedure in place, if there isn't such regulatory system in place, then maybe that's already a no-go, and you should aim at resolving those challenges first. From a technical standpoint, I would say that in many ways there isn't so many technical challenges because you know those wells already. You've already been producing from the system for many years already. There shouldn't be surprises. It's really about how much it might cost you to do the retrofit, and will you have the cash back to cover those costs, and how quickly can you have the cash back? Another question. What is the main factor that most affects cost of transforming the wells into geothermal wells? Well, I think we already covered that, talking about what level of retrofit you might need to do versus how many revenues you expect to be making from the conversion. This is an interesting one. Is it most economic to drill a new geothermal well or to transform an oil and gas well? It's a very interesting question because, yes, it is possible that in some cases it might be more straightforward, cheaper, and maybe environmentally safer to go straight for a brand new dedicated geothermal well. That's if you have, of course, a pure geothermal resource in place, that is an aquifer, for example. If not, it depends on the advantages you may have in continuing operation from a given site where you've already spent capex and opex over the years. So it's all done once again to the individual case. We cannot generalize this sort of conclusions, but I like the question because if you have the option to do either or, and if you're thinking exclusively about geothermal production and no longer about hydrocarbon co-production, then it might be better to start afresh. So I thank you for your virtual attention. I also thank you for your virtual questions, and I hope I was able to address them as best as you wanted them to be addressed. This topic is incredibly interesting. I think it's something that is highly contemporary. I think it is something that we will hear more and more about in the next few years, and I'm pretty sure, I'm very confident that a few projects will materialize. And as long as we remember to take a case-by-case approach, and as long as we are thorough with our feasibility studies, and as long as we have the support of the local authorities and the local governments to resolve any gaps in regulatory policies, then I'm sure we will see these projects. So thank you once again, and all the best to all of you. Bye-bye.